Nowadays, many artists try to design similar kind of artworks, but making such design manually is difficult and tedious. Developing computational methods to achieve this is also challenging. One possible way is to dock the two shapes at every possible position and every scale. This involves a gigantic search space. Our work addresses this problem and performs this originally intractable plane filling problem in a tractable manner. This is achieved by a brand new shape descriptor, Pyramid of Arclength Descriptor, in short, PAD. Its primitive element employs a pyramid of arc length values. It describes the local shape around a point in a rotational, scale-invariant manner. With PAD, 99% of unnecessary docking choices can be avoided. To understand PAD, we consider a basic case first, a circle. Imagine we distribute packed dots at equal arc length intervals. As the arc length is not scale invariant, the larger the circle, the more the packed dots we will have. To design our descriptor, we need a quantity that never changes even with a scale, such that the same shape in different scales can have the same description. Fortunately, there exists a scale invariant quantity. It is the integral of absolute curvature. The arc length and curvature of a shape change inversely according to its scale. Hence, the influence of the scale can be cancelled out. By putting cherries at equal intervals in the scale invariant domain, there will be more cherries distributed in a curved portion than in a flat portion. We employ this domain to design our local descriptor. One straightforward idea is to count how many cherries inside a fixed interval. But this idea doesn't work as it becomes scale dependent. Instead, we design a different approach. Given a target number of cherries, how far should we go to collect them? We first consider one target cherry along one direction from a point. When we obtain sufficient number of cherries, the interval that the Pac-Man traversed is considered as the first element of our PAD. This interval is rotational invariant and can be normalized to be scale invariant. However, one element is not sufficient to distinguish shapes. Hence, we consider a pyramid of intervals with increasing numbers of the target cherries, such as 2, 4, 8, etc. Next, we do the same for the other direction to obtain another set of intervals. The combined intervals form our PAD. Please refer to the paper for details. By using our PAD, we can obtain the best matching with the longest shared arc length. We may directly employ it for plane filling. However, arc length maximization may not be the only criterion for aesthetic purpose. We should consider other criteria, such as penalizing the overlapping and gap between the two shapes. Here is a result generated with this objective. Moreover, we can have scale and orientation constraints by penalizing candidates whose size or orientation exceeds the preferred range. Hence, we can generate results with desired scale ranges and avoid candidates that are upside down. Here we show more results, a doodle with line arts as a 2D shapes. A cyclic scrolling image where its left and right sides tiled seamlessly. We also develop an optional deformation step to produce seamless tiling in the final result. Thanks for watching this video.